In this lesson, we will discuss principal ideal domains, or PIDs. So in a previous lecture, we showed that every ideal of a Euclidean domain is principal. So domains with this property are called principal ideal domains. So a principal ideal domain or PID is an integral domain in which every ideal is principal. So in the last lecture, we proved that every Euclidean domain is a PID, principal ideal domain. So in particular, rings like the integers, this is a Euclidean domain. And we've also proved directly that it's a principal ideal domain, but is therefore a PID. We also showed that for any field F, that the polynomial ring F adjoint X is a Euclidean domain, and then similarly we must have that this polynomial ring is a principal ideal domain as well. So recall that maximal ideals are always prime ideals, but the converse is not true in general. However, when we're in a principal ideal domain, we do have this property. So this leads to the following theorem. Every non-zero prime ideal in a principal ideal domain is a maximal ideal. So for the proof, let's let the ideal generated by P be a non-zero prime ideal. In a ring R, which is a PID, and let's let I be the ideal generated by M be another ideal that contains the ideal generated by P. So let's be any ideal containing the ideal generated by P. So in order to show that the ideal generated by P is maximal, we're going to show that I either equals the ideal generated by P or I equals the whole ring R. Okay, so since P is in the ideal I, which is the ideal generated by M, we can write P as a multiple of M. So we have P equals Rm for some element R in the ring. Since this ideal is prime and Rm, which is equal to P, is in the ideal generated by P, then either R is in P or M is in P. The ideal generated by P. So if M is in the ideal generated by P, then I is the ideal generated by M must be contained in the ideal generated by P, and hence I must equal the ideal generated by P. So if, however, R is in the ideal generated by P, then we could write R as a multiple of P. So then R equals, say, PS for some element S in the ring. Then P, which equals Rm, can be rewritten as P times S times M. But recall we're in an integral domain, so we have the cancellation law. So if P equals P times Sm, then that implies that by cancellation, 1 equals Sm. By cancellation in integral domain R. Then M is a unit in I, which is the ideal generated by M, and hence I contains a unit and is therefore equal to the whole ring R. So this shows that the ideal generated by P is maximal, and it concludes the proof of the theorem. So we have shown that every Euclidean domain is a principal ideal domain, but the converse is not true. So not every principal ideal domain is a Euclidean domain. We're not going to show all the details, but it can be shown that the quadratic integer ring Z adjoin 1 plus the square root of negative 19 all over 2. This is a principal ideal domain that is not a Euclidean domain. So every Euclidean domain is a PID, but every PID is not necessarily a Euclidean domain. So we're building up to showing that every PID is actually another class of domain called a unique factorization domain. But now we're going to define some new terms in order to extend the idea of a unique factorization in the integers to this larger class of ring called unique factorization domains. So now we're going to develop all the terminology necessary for studying UFDs. So let's begin with some definitions. So R is going to be an integral domain. So that is, R is a commutative ring with identity and no zero divisors. For our first definition, let's suppose that little r is non-zero and is not a unit. In R, then R is called irreducible in R if whenever R equals a product AB, AB in the ring R, then at least one of A or B must be a unit in R. R is irreducible if whenever you write R as a product, one of the factors must be a unit. Otherwise, we say R is reducible. Secondly, the non-zero element P in R is called prime in R if P is not a unit and P divides A times B implies P divides A or P divides B. Thirdly, we're going to define what it means for two elements to be associates, that is, if they differ by a unit. So two elements, A and B of R, are called associates. Or we say A is associate to B in R if A equals some unit times B. Some unit U in R. We see that A and B are associates if they differ by a unit. So next we give some results using these new definitions. First, we prove that in an integral domain, a prime element is always irreducible. Let's suppose that P is prime and let's write P as the product A times B. So in order to show that P is irreducible, we must show that either A or B is a unit. Well, we know that P is prime, so we know that either P divides A or P divides B. So without loss of generality, let's just assume that P divides A. And hence we can write A as a multiple of P. So let's write A as P times C for some element C in the ring. Then P is A times B, but I can write A as P times C times B. And by cancellation, we have 1 equals C times B. So thus B is a unit. And that proves that P must be irreducible. So we've just shown that in an integral domain, a prime element is always irreducible. Now the converse is not always true in general. So it is not true in general that an irreducible element is always prime. So for example, in the ring R, which is the quadratic integer ring Z adjoined square root of -5, the element 3 is actually irreducible in this ring R, but 3 is not prime because 3 divides 9, which is the product of two elements, 2 plus square root of -5 and 2 minus square root of -5. But 3 does not divide 2 plus square root of -5, and 3 does not divide 2 minus square root of -5. So although 3 divides a product, it does not divide either of the factors, so 3 is not prime in this ring. So in a few minutes we'll show that 3 is irreducible in this ring. And this example just shows that irreducible elements are not always the same as prime elements in a given integral domain. But we will show now that in a PID, irreducibles and primes coincide. In a PID, a non-zero element is prime if and only if it is irreducible. We've already proven the forward implication, that is, we've already proven that prime elements are irreducible. So it remains to prove the converse. I'm going to show conversely that if P is irreducible, then P is prime. So to this end, let's let R be a PID. And suppose P is irreducible. In R, and P divides the product AB. So in order to show that P is prime, we need to show that P either divides A or P divides B. So I'm going to show that P divides A or P divides B, and then that'll conclude the proof. To do this, I'm going to define an ideal I as the ideal generated by A plus the ideal generated by P. So we've proven that this is actually an ideal, and since we're in a PID, this ideal I is principal. So then I is principal. And I can write I as the ideal generated by some element D. Then, in particular, the element P is in this ideal I. And so therefore we can write P as a multiple of D. P equals dr for some R in the ring. Now we're going to use the fact that P is irreducible. So since P is irreducible, and I've written P as a product, dr, we know that one of D or R is a unit. D or R is a unit. If D is a unit, then D is contained in the ideal I, and since I contains a unit, I must be the whole ring R, and hence the identity must be in the ideal I. Recall that I was the ideal generated by A plus the ideal generated by P, so that means that 1 can be written as A times some element X plus P times some element Y. For some elements X and Y. And then if I multiply this equation by B, I have B equals ABX plus PBY. And if we look on the right-hand side, we know that P divides AB, and therefore P divides both terms on the right-hand side, and therefore must divide the whole sum, which equals B. So since P divides both terms, on the right, P divides B as well. So we see that if D is a unit, then P will divide B. Now we'll conclude by showing that if R is a unit, then P will divide A. So if R was in fact a unit, then the ideal generated by P is equal to the ideal generated by dr. But if R is a unit, then that's going to be the same as the ideal generated by D, which is I. So we see that the ideal generated by P is the same as I. We know that A is an element of the ideal generated by A. So it's also an element of the ideal generated by A plus the ideal generated by P, which is I, which we just showed is the ideal generated by P. So we see that A is in the ideal generated by P, and we can write A as a multiple of P. So let's write A as PT for some element T in the ring. But this is the same as saying that P divides A. So we've shown that in either case, either P divides A or P divides B, and hence P must be a prime element of the ring. So we've just shown that in a PID, the prime elements are the same as the irreducible elements. So this last theorem again shows that the ring is not a PID, because if it was a PID, then every irreducible element would also be prime. But as I claimed earlier, 3 is irreducible but not prime. Since 3 is irreducible, but not prime in this ring. So let's show that 3 is irreducible. So suppose I could factor 3 as alpha times beta for some elements in the ring, such that alpha and beta are not units. And we're going to use the field norm to prove that this is impossible. So using the field norm N, defined by N of A plus B squared negative 5 will equal A squared plus 5B squared. So we have 9, which would be the norm of 3, but that's going to equal the norm of alpha beta. But since the norm is multiplicative, this is equal to the norm of alpha times the norm of beta. Now we're dealing with integers here, so the norm of alpha and the norm of beta are positive integers. And these are positive integers that divide 9. They must equal 1, 3, or 9. Now, recall we're assuming that alpha and beta are not units, so therefore their norms cannot equal 1. So since alpha and beta are not units, their norms can't equal 1. So we showed earlier that the norms of units are either plus or minus 1. In this case, it would have to be 1. So if the norms of alpha and beta can't equal 1, they can't both be equal to 9, because 9 times 9 would not equal 9. And the only possibility left was that they both would have to equal 3. So thus the norm of alpha must equal the norm of beta, and that must be equal to 3. This is the only possibility if alpha and beta are not units. So let's look at alpha more carefully. So let's let alpha be a plus b square root of negative 5 for some integers a and b. Then a squared plus 5b squared is the norm of alpha, which is equal to 3. But if you look at alpha a and b, there's no integers a and b such that a squared plus 5b squared can equal 3. So this equation does not have any integer solution. Which does not have any integer solutions. Thus, one of alpha and beta must be a unit because one of their norms must equal 1. And if one of alpha or beta is a unit, that means that 3 must be irreducible. So the only way to write 3 as a product of elements alpha beta is if one of them is a unit. So we now have all the terminology to define a new class of rings called unique factorization domains. This will be the next topic that we should discuss.